Starting in chapter 10, we're going to lead off with parametric functions. And a parametric equation has a third variable, and usually the variable is t. Sometimes it can be other variables, but usually it's t, and a lot of times that's for time. And this t is called the parameter. Example 1 wants us to sketch the parametric curve and then write a rectangular equation. Rectangular just means no t's in it. So I'm going to start off by looking at what they gave me. I can see that I have probably the easier part, y equals t over 2. So I'm just going to start with the y here, look up at the t's, and just divide all these numbers by 2. So that's negative 1, negative 1/2, still 0, 1/2, 1, and 3/2. Okay, same thing, I'm going to go with the x this time, which will be t squared minus 4. Let's start here in the middle. 0 squared minus 4 is negative 4. 1 squared, that's 1 minus 4 is negative 3. Plugging in the 2 gives me 4 minus 4. And putting the 3 in would be 9 minus 4, that's 5. And then I can use symmetry to go the other direction. The negative 1 and the negative 2 are going to give me the same answers that the positive 1 and the positive 2 gave. So the table is set. Now using the table, I'm going to graph the curve. I'll do that in red. So if you look at your xy coordinates, you have 0, negative 1. You've got negative 3, comma, negative 1/2. That's right here. Negative 4, 0. Negative 3, positive 1/2. Looks like a sideways opening parabola. 0, 1. Finally, 5 would be 1.5. And so this is going to go in this direction right here. And because we have a limited domain, we don't go on forever. We stop. And then it's customary to also show what direction we're traveling in as t increases. So I put these little arrows on my drawing to show the direction or the path as I go from time equals negative 2 to time equals 3. So that is the sketch of the curve. And then finally it says write the corresponding rectangular equation. To do that, I'm going to start here with this blue equation and solve for t. So I will end up having t squared equals x plus 4. That's if I add 4 to both sides. Let's curl this t so it doesn't look like a plus. And then finally I'll square root both sides. So t is going to be plus or minus the square root of x plus 4. Okay, so there's that. Now switching over here to green, I've got my y equals, and it's t over 2, so I just simply take the t that I have, which is the plus or minus square root of x plus 4, and I'll just put a 2 on the bottom, or if I prefer, I can put a 1/2 in front. It means the same thing. And that'll be the answer in rectangular form. So it's a rectangular equation. Notice that the t has been removed. The parameter has been removed. So that's example number 1. In example number 2, we also want to eliminate the parameter. There's no chart this time, but we still want to make a graph and get a rectangular equation. Whenever you have sines and cosines, there's a little different approach to it. You want to get the cosine of theta and the sine of theta by themselves. So I'm going to do that first. Okay, once I do that, I can square both sides. So if I square here, cosine squared, and I square this side, I'll have x minus 4 squared over 4. On the other equation, if I square the sine, I have sine squared. If I square the right, I have y plus 1 squared over 16. And keep in mind that sine squared theta plus cosine squared theta equals 1. So that allows me to say this. X minus 4 squared over 4 plus y plus 1 squared over 16 equals 1. And that is your rectangular equation. Notice the theta, which is the parameter in this problem, has been removed. And if you go ahead and graph it, you're going to find that you should be able to recognize this from honors pre-calc. It's an ellipse. The center is at 4, negative 1, which is right here. And then the 4 means that I go 2 in each direction out along the x-axis. And now I go up and down 4 on the y-axis because that's the 16. That's 4 squared. And that's my graph. So again, on this number 3, you want to go ahead and isolate the trig. So this time first, I think to make it easier, I'm going to square both sides. So the x will become x squared, and obviously the right will be squared as well. Then we'll go ahead and divide by 16. I think I'm going to put the secant squared first. That looks pretty good. And then I'll do the same thing over here on the right. I'm going to go ahead and square both sides. So y squared equals 9 tan squared theta. And dividing by 9, and I'll rearrange. So I'm going to have tangent squared. The theta is y squared over 9. Now remember that tangent squared plus 1 is secant squared. So we have tangent squared, that's this, plus 1 is secant squared. Knowing that, we go ahead and use our Pythagorean identity. So we have tangent squared of theta plus 1 is secant squared of theta. And just plug in what we know. Remember we said that tangent squared was the y squared over 9. The secant squared was the x squared over 16. Our final answer is right here. Again, notice the parameter. In this case, the theta is gone. It's a hyperbola. It's opening left and right because the x squared is the positive term. And you can see the basic setup will look like this. You can see that, again, like I said, the center is at 0, 0. You're going to go 4 out in the x direction and 3 out in the y direction to make your box, your asymptotes. And then the parabola will just, the hyperbola will just follow along. So this is going to be your equation. It's hyperbolic. All right, so we've eliminated the parameter, and we've got the rectangular equation written and graphed. So that's number 3. That's really it for pre-calc at this point. Now we're going to move on to the actual calculus. In Chapter 10, you're going to be expected to know the formulas for taking derivatives of equations in parametric form. The first derivative is pretty straightforward. dy dx just makes sense. You can see the dy dx in the formula. You're just taking the derivatives with respect to t first. So it's dy dt over dx dt. It almost has the illusion that the dt's somehow cancel each other. And really there's a bit of truth to that. So that's not bad. Then it starts to get weird. You come down to the second derivative, and you take the dy dx that you just got. The dy dx that you just got right up here, you take the derivative of it normally with respect to t, but then the dx dt makes a repeat cameo appearance. In fact, dx dt is always in the denominator every single time you take a derivative. Whether it's the second derivative, third derivative, fourth derivative, you still have to divide by dx dt. Speaking of third derivative, when you take the third derivative, you're going to go ahead and start with the second derivative that you just found. You'll take its derivative with respect to t, but then again, you're going to divide by a dx dt again. It's easier, I think, if you see some examples, but that's the basic formula set that you're going to need to know. Number 4, find the derivative, second derivative, and third derivative of y with respect to x, but we have some parametrics. I went ahead and I took the 3 formulas I just introduced and I recopied them down on the left so we kind of had a bit of a cheat sheet to work with. So we're going to start with our dy dx. I'll use red for this one. dy dx, of course, is equal to dy dt, so I take the y equals equation. That's going to end up being 42t to the 5th. Let's write that down. Over dx dt, which is, of course, this equation. And that's going to be 8t. It's a good idea to get this dx dt correct because you're going to be reusing it all 3 times. So if you miss it once, you're going to miss them all. So far, so good. I'm going to simplify this down. 42 and 8 are both even numbers. You can cut them in half. So it's going to be 21 fourths. And then, of course, it's t to the fourth. You just subtract the exponents there. And that's your first derivative, dy dx. Now, normally I say that if it's dy dx, you want your letters in terms of x's. But with parametrics, a lot of times College Board will just say, hey, give it in terms of t. That's fine. If you have to substitute the x's back in for the t's, that's easy enough to do. You can use this, first equation right here to do so. But I'm okay if you leave it like that. All right, next up, we're going to take the second derivative. So what you do is you take the first derivative that you had just now, and you're going to take its derivative. And what I mean by that is you've got this answer right here, this 21 fourths t to the fourth. Let's take its derivative. Do that right here. Well, obviously, exponent times coefficient, the 4's are going to cancel. It'll simply be 21, and then it's going to be t to the third, down by a power. But since it's parametric, you still have the dx dt at the bottom. Remember, that was 8t, and it still is 8t. And so simplifying that will give us our answer of 21/8 t squared. And that's our second derivative, dy dx, second derivative. And finally, for the third derivative, I'm going to go ahead and switch to blue. We'll take the derivative right here of this green part. So again, the 21/8 times the 2 will be 21 fourths. This is in the numerator. T to the first. And again, we're still dividing by dx dt, which is the 8t. In this case, the t's are going to cancel out. And if you simplify that fraction by multiplying numerator and denominator both by 4, you get 21/32. And that's your third and final derivative. I could have you take more derivatives, fourth, fifth, sixth derivatives, but they'd all be zeros because the blue answer is a constant, and we know already that the derivative of a constant is 0, even in the parametric world. So there you go. That's example number 4. A natural question would probably be, why are we doing this? Well, as you know, your graphing calculator only graphs functions, and a lot of times things that we want to graph normally wouldn't be functions. They'd fail the vertical line test. In physics, as you know, your horizontal and your vertical forces are independent of each other, and so a lot of times parametric equations are useful. We also saw this in honors pre-calc when we were, hurling cannonballs through the air or kicking soccer balls or just, seeing how things free fall. We would use parametrics, and it was really helpful. You probably wonder, why do we keep dividing by this dx dt on the bottom? It seems strange. I'll show you why it works. I just did a quick proof. If you take the first derivative, say we know dy dx already. I'll kind of box it in red. If you take the derivative of dy dx, it's really the derivative with respect to x of dy dt over dx dt. We saw that already. That seems pretty believable to most people. The thing that they don't get is, why is this dx dt on the bottom? That seems odd. Well, the way I can answer that is, if we want dy dx, and you're taking dy dx, but suddenly you have t's, you're using the wrong letter, so you need a chain rule. Sometimes they call it a forgiveness parentheses, and that's right here in purple. It's like, I know it was a t, it was supposed to be an x, dt dx. So you have that on the end. But rather than multiplying by this thing, we can divide by the reciprocal, so we just flip it upside down, and that makes the formula that we've been using. And that's why we have the extra dx dt in the denominator on every step when we're using parametric derivatives. Hopefully that helps. I don't know if that was the smoothest explanation I've ever given, but hey, it works. Number 5, we're going to find first and second derivatives. Then we're going to find the slope and the concavity. And of course, as we well know, slope goes with the first derivative. And if anybody ever asks you about concavity, that's going to go with the second derivative. All right, so we'll start out with the first derivative first. And I've got my formulas off to the side. dy dt would simply be 8. And dx dt is going to be 6t. And I can simplify that down, of course, to 4 over 3t. You don't want to call it 4/3 t, otherwise your t's in the numerator. So 4 over 3t is the first derivative, so I define that. And then the slope will be easy. They just want t to be equal to 2, so you can just plug the 2 in, and you can see that that would be 4 over 6. And of course, 4 over 6 becomes 2/3, so the slope at that location is 2/3. All right, so we're halfway done. We've done all the purple stuff. Now we'll do the second derivative and talk concavity. Okay, first off, we'll start by taking this first derivative that we found. I want to think of this thing as 4/3 t to the negative 1. That'll make it a little easier. So the derivative of that will be negative 4/3 t to the negative 2nd. Exponent times coefficient, down by a power. Again, dx dt is still 6t. That has not changed at all. Just have to move it down. We can simplify that down just a bit. Let me fix it up over here. Make a little more room for myself. The numerator is going to be negative 4 over 3t squared. We're dividing by 6t over 1. That's the same thing as multiplying by 1 over 6t. You can do a little bit of canceling, at least with the 4 and the 6. Just cut them in half. That'll be negative 2. That's a 3t. And if you multiply that together, you're going to end up with negative 2 over 9t cubed. Okay, so that's the second derivative. And again, we want to find the concavity when t is equal to 2. So again, we'll place the 2 into this green square and see what we have. And as you can tell, it's going to be a negative answer. In fact, it's going to be negative 2 over 72 or negative 1/36. And so since the second derivative is less than 0, it is concave down. And that's what I wanted in example number 5. Okay, here in number 6, we're looking for the same thing. We want first and second derivatives, we want slope, we want concavity. So we'll start out with the first derivative. I'll keep the purple color rolling. dy dt. Sine squared of theta is really sine of theta squared. I like to write it that way a little bit better. I can see what I'm doing. 2 times 1 is 2 out front. Sine of theta is now to the first. And then finally, a chain rule is going to be cosine of theta. So 2 sine theta cos theta, you may already recognize that as sine of 2 theta. That's going to be very helpful. The denominator, dx dt, the derivative of cosine of 2 theta is negative sine of 2 theta. But then there's a chain rule too, which I'll slip into here. So far so good. Again, I realize that, as I just mentioned, the numerator here, 2 sine cosine, is really sine of 2 theta. And so sine of 2 theta will cancel its counterpart, leaving you with simply negative 1/2 for the first derivative, which is really astonishing. And obviously, if the first derivative is negative 1/2, so is the slope. So I kind of get a 2 for 1 there. And heck, if the first derivative is a constant, negative 1/2, the second derivative is 0. And so that's super easy, which means as far as the concavity goes, it's neither concave up nor concave down. The original parametric equation happens to be linear. On to number 7. Directions have changed just a bit. It says find the equation of the tan line to the curve at each given point. They've given us a couple different points. Equation of the tangent line. Okay, well obviously with the equation of the tangent line, We have the x and y points. We just have to figure out what the slope is. And the slope, of course, is dy dx. Going into parametric form, we can change the dy dx to dy d theta over dx d theta. Let's see what those are. Starting with dy d theta, it's right here. The derivative of 5 sine of theta is 5 cosine of theta. And the dx d theta, the derivative here, would be negative 12 sine theta. Now, if you want, you could call that negative 5/12 cotangent theta. I think I'm going to leave it as is. That'll be a little bit easier. And then we have to figure out the two different tangent lines. Let's go ahead and start with the easier one, which I believe to be the negative 12, 0 at the end. I'll do that in blue. Remember that the negative 12 is the x, the 0 is the y. So starting out here, we've got y minus 0, which is completely unnecessary, equals slope, which I'm going to leave blank. And to find the slope, we'll just take the theta and we'll plug it in. The problem is, I don't know what the theta is. But I do know that x is negative 12. And that's something, so let me write that down. X is negative 12. But I also remember that x is 12 cos theta, so I can bring that in. So instead of an x, I'll replace that with a 12 cosine theta. It's equal to negative 12. Divide both sides by 12, you get cosine of theta equals negative 1. Cosine of what is negative 1? Well, of course, that's going to be 180 or pi, 180 degrees. I think I'll stick in radians. Okay, so theta is pi. So I pop that pi back in for the angles so I can get my slope. 5 cosine pi. Cosine of pi is negative 1, so that's going to be negative 5. The denominator, I have negative 12 sine of pi. That's 0. Uh-oh. Negative 5 divided by 0 is undefined, which means this is a vertical line, which means I got to bail out of my point slope form altogether. And so the line is simply going to be x equals something. And I already know that x equals negative 12, and that is the tan line. So that is one answer. X is negative 12. All right, let me erase everything except for the red, and then we'll go to the other point. We'll do that in green. We'll find the tan line here at 6 comma 5 rad 3 over 2. Okay, the other tangent line, let me go ahead and try point slope form again. It's going to be y minus 5 rad 3 over 2. A little bit ugly, but that's okay. Equals, I leave a blank for the slope, x minus 6. Okay, I'm just taking the x and y from up here, from the green point, if you will. And now I've got to figure out, okay, what is theta? Oh, man. Again, I can use either one. I think I'm going to stick with the x. That worked pretty well last time. The x is 6. So let me bring that down here. X was 6. Remember, x is also 12 cos theta, so 12 cosine theta is 6. Divide by 12, cosine of theta is going to be 6/12, or 1/2. And even though cosine of theta equals 1/2 in two different quadrants, we're sticking with quadrant 1 because, as you notice, the point that this came from, both x and y were positive. So I'm going to stick with 60 degrees or pi over 3 in radians. So that's my theta down here. And I'll take it up here to the red. We'll put in the pi over 3 and see what we come up with. This is going to get a little obnoxious. I'll come down here to the corner. The slope is going to be 5. Cosine of pi over 3 is 1/2. So 5 times 1/2 over negative 12. But the sine, unfortunately, is rad 3 over 2. That's going to be 5/2 over negative 6 rad 3. which will rationalize into negative 5 rad 3 over 36. I'll put that into my answer and I'll be all finished.